Hello, everyone. It's Ben Marlin once again, and this is a video for the Calc 3 coverage of the idea of the direct comparison test. So the direct comparison test, as you'll read in your text, states that if you have two positive series, summation of the A sub n's and summation of the B sub n's, if you know that each A sub n is greater than its corresponding B sub n, and the B sub n's are greater than 0, if the series, the summation of the A sub n's converges, then the summation of the B sub n's must also converge. If you have something that's convergent and something that's smaller than it, then that thing has to converge as well. But on the other hand, it also says if you have that situation, A sub n is greater than B sub n is greater than 0, and you know that the summation of the B sub n's diverges and goes to infinity, this thing that's bigger, the summation of the A sub n's, also has to diverge. Okay? So the thing that will be the hardest work on this is actually figuring out what things to compare stuff to. Now, mostly the things that you compare to are the series you already know whether they converge or not, namely all those p-series stuff and the geometric series. Those are the easiest ones to do comparisons with. Additional to that, I would say anything that you've already shown converges or diverges using the integral test, then you can also do a comparison to that. So that's how this builds on itself. You know, you learn how to show whether one thing converges or diverges. It shows you how another thing and another thing and another thing. So it just all builds together. So let me, as our first example here, show you one that we already know the answer to. I always kind of like to start with one we know the answer to and then make it more complicated as we go along. And okay, and so the thing we're looking at is the summation of 1 over n squared plus 1. If you remember, we already checked with the integral test and saw that it converged. But one thing that people will frequently do is to look at this and say, aha, that's a p-series. It's not. It's similar to a p-series. It's not quite a p-series, right? So if you're looking at that and saying that looks a lot like the summation n equals 1 to infinity of 1 over n squared, you're right. Those are very similar. This one we know converges by our p-series ideas with the p equaling 2, which you just needed to have the p-value be greater than or equal to 1. Sorry, I hit the wrong button there. You have to have the p-value be greater than 1 in order to have it converge. So what you have to spot here then is that 1 over n squared is greater than 1 over n squared plus 1. If you're thinking, gosh, I don't really spot why that is, it's simply that when you have a fraction and you make the denominator bigger, then you make the result smaller. So any place that you have some addition into a denominator like that, you're making something smaller. So we can get to the conclusion here that summation n equals 1 to infinity of 1 over n squared plus 1 converges by the direct comparison test. Okay, we'd already seen it converging using the integral test before, but now we have just another way that you can go at that. And please understand that when it comes exam time, or if you're trying to write something that depends on this in the future, you can use either one, whichever works best. Okay. As a matter of fact, we'll come up with maybe a couple of other ways that we can see that one later on. All right, let's look at an example where we go the opposite direction. Okay, we have one that is going to actually diverge, but we see it by comparing it to something that is smaller than it and also diverges. So taking a look there, that 1 over log n, if you were to take and replace the 1 over log n with just a plain 1 over n, which we know that that one diverges by p series with the p being equal to 1. And our criteria says that when it's 1 or smaller, that it diverges. So what we have to do here is to work out a little bit of something. And there is a tricky bit to it, okay? The first thing I want you to be able to spot is that when you take the logarithm of something, that the result you get is smaller than the n. If I do a quick sketch over here to the side, you know that the log function looks somewhat like this, and the y equals x function looks somewhat like this. And that says that the log function is always less than the actual x value, in this case n value, but we are going to have those be positive because the only n values we're plugging in is 2 or larger, okay? So then when we take reciprocals, something funny happens. When you take reciprocals, the bigger number, its reciprocal is smaller. So that means 1 over log n will be greater than 1 over n. So that lets us conclude that our summation of 1 over log n diverges by the direct comparison test. So hopefully that makes sense, and that gives us an example of how to use this in either direction. If you've got something that looks kind of like a p-series, the degree of the denominator being larger than the degree of the numerator, then you can kind of get this kind of estimation going. We will use something called the limit comparison tests next, and those limit comparison tests will give us just a little bit of a different way to tackle that, okay? But if you can see that you're just adding or subtracting something from a denominator, adding or subtracting something from a numerator, then the direct comparison test is fairly straightforward to use, okay? All right, let's look at one that's a little bit trickier to figure out how you're going to use it. And so this one, as soon as it brings it up, this one has a 1 over the square root of n and then times an n squared plus 1. So in your mind, you might be saying, that could be like a 1 over the square root of n, or it could be like a 1 over n squared. So how do I know which one to associate it with? Well, the thing we have to spot is that because we have our n values always being greater than or equal to 1, then a square root of n will also be greater than or equal to 1, and 1 over the square root of n. So taking reciprocals there, that will end up being something that is less than 1. I don't like how I wrote that, so forgive me as I rewrite it in the other order, so that we'll have 1 is always greater than or equal to 1 over the square root of n. If you've never dealt with mathematicians before, we are all a little bit OCD. So, but that's because, just like the previous example, when you take reciprocals of positive things, it switches the order, okay? So the reason that that's important is that now we can say that 1 over n squared plus 1 would have to be greater than 1 over the square root of n times the n squared plus 1, because what we've done is to multiply by a fraction that's smaller than 1. It makes it something smaller, okay? And that's going to turn out to be positive. Now, you might think, hey, I could tackle this the other way. I can also say that 1 over n squared plus 1 is less than 1, so this is less than 1 over the square root of n. but the summation of the 1 over the square root of n diverges. And having something that's smaller than a divergent series doesn't tell you anything. But since the summation of 1 over n squared plus 1 converges by the integral test, then summation n equals 1 to infinity of this thing converges by direct comparison test. We have something that is smaller than a convergent series, and that it means that we've got something convergent. If we have something that's bigger than a divergent series, then we would know that it's divergent, okay? So that's a little bit of our motivation here of how to choose what to compare to. So let's launch straight into this next example here, which also you have to pick what to compare to. And so the thing that you should think to compare this to is summation n equals, now it says 2 there, so let's go ahead and say 2 to infinity of 1 over n, okay? The reason you make that connection is that you've got a square root of a square, so it's probably going to be something along the lines of just an n power. Sorry, just a first power of n. So we know that this one diverges. And I'll jot down that that's in the p series. And the thing that we have to spot here is what goes on with that term there. So we know that if we had just a square root of n squared, since we're always dealing with positive stuff, that would be equal to just n. So if we take a square root of n squared and inside there subtract something, now it's no longer equal, but since we subtracted something, that'll be smaller. And then when we take reciprocals, we will get something that's larger and still greater than 0. So summation n equals 2 to infinity 1 over n squared minus 1 in the square root diverges by direct comparison test, okay? And so I wanted us to spot that this over here, we wouldn't be able to do the same kind of thing, because when we came in here and said, all right, my square root of n squared plus 1 is going to be greater than n, and then I took reciprocals, I would have the 1 over the square root of n squared plus 1 is going to be less than 1 over n. So smaller than a divergent series. It might be divergent, it might be convergent. It'll actually be divergent, but we're going to wait a little while to see that, okay? All right, then last example that we've got here, I've got 2 series that look a little bit alike because they're doing something with a geometric series and then tied together with something that changes a little bit. So if you take a look at this first one here, you could figure out that that one diverges just by taking the nth term test. We can do the limit as n goes to infinity of n 2 to the n, and you know that's going to be infinity, which is not 0. So our series diverges by the nth term test. I think your textbook refers to that as the Leibniz test or Leibniz test. Sure, you can call it that if you want to, but this is the first textbook I've ever ran into that uses that terminology. Everything else, every other textbook always refers to it as the nth term test. So in any case, though, you could also have seen this by spotting that n 2 to the n is greater than 2 to the n, or that it's greater than n, either way, and then using a direct comparison term sort of thing with it. This one over here, the thing that you're going to want to look at is that if you threw out the n part in that, that this would be 2/3 to the nth power, right? And so since 2/3 to the nth power would be greater than this, and I need you to spot there, we're multiplying something bigger than 1 in the denominator, and that makes the denominator bigger, which makes the fraction smaller, okay? So since summation n equals 1 to infinity, 2/3 to the n converges, and by geometric series, with the r being less than 1 in absolute value. And then we can conclude that the summation n equals 1 to infinity, 2 to the n over n, 3 to the n converges by direct comparison test. Yay! And that gets us our examples, all right? So next thing we'll talk about, it's going to be limit comparison test stuff. Very similar, but maybe a little bit easier, okay? So I'll see you then.